Welcome to Complexity Made Simple, and in this video newsletter what we're going to take a look at is how a design of experiment can help you to predict your CpK. So this isn't just optimizing the process. We can predict the CpK, potentially make a prediction before we run the confirmation test. So I'm going to show you how that gets done, in particular with SPCXL and DOE Pro. So let's take a look at this. DOE, I'm just going to say DOE equals CpK because we're going to use the design of experiments. We're going to use the information coming out of the model to predict the CpK, but also, by the way, to make some different business decisions. So you will see the power of the model gives you the ability to make different decisions and then evaluate the cost. By the way, anybody that says AI can do this, this is something AI could never do, because you're evaluating different business benefits, different business losses, context that a computer can never know. So let's get into this. So what we have is a DOE. Now it happens to be a Taguchi L12 screening DOE. So what you're going to see me do is you're going to see me model with the L12. Now I have to say, modeling with the L12 isn't something I would recommend, but this particular client, this is real data, this particular client, they want to try and save some time. So we've said, let's do the model with the L12. If the model works, brilliant, we don't have to do the full factorial. But I'm going to show you a Taguchi L12. I'm not going to tell you necessarily what the process is, obviously, or what the client is. We're just going to go through it. I'm going to talk about what the targets are, and then I'm going to show you how we take the data from the DOE and predict the CpK. So let's take a look. Let's have a look on the computer at the L12, do the analysis, and I'll show you how this is done. Okay, so here's the L12. Now you can see at the bottom we've got three sheets. CTQ1, so there's a dimension 1 that they're trying to hit, there's dimension 2 that they're trying to hit, and there's a cycle time that they're trying to hit. So adding the cycle time in, of course, makes this designed experiment so much more intelligent. Now, because it's a Taguchi L12, the first analysis that I'm going to do is just a graphical analysis. I'm going to create something called marginal means plots, sometimes called graphical plots. So let's do that. Analyze design, marginal means plot, both the Y and the S. And I get two graphs for CTQ1. Okay, so one that tells me about standard deviation, one that tells me about the noise, the signal. So one that tells me about the signal, the mean, one that tells me about the noise, the standard deviation. So that's CTQ1. Now I'm going to generate the same graphs for CTQ2. Okay, so I've got the graphs now for CTQ2. Standard deviation graph, means graph, average graph. Now, in order to be able to see these cleanly, what I usually do is I pop these out onto a PowerPoint sheet, put them on the same page so that we can see what's going on. So let's do that now. This is the standard deviation response of that L12. So we had 6 variables: fixed temperature, moving temperature, cooling time, holding pressure, injection speed, and holding time. 6 variables, and the effect on CTQ1, the effect on CTQ2. Now, just to clarify practically what this graph is telling you, it's telling you that you can have this effect. So if you put your setting to the top of the blue line there, which would be this variable at 80, maybe you'll get this standard deviation, this spread. But if you choose to wind the blue variable all the way to the bottom and you minimize standard deviation, what will you do? You turn the standard deviation down, make the process more consistent. So you're removing the spread from the data. That's what the S diagram is telling you. If you were looking at this on a graph, the red data might look like that, and the blue data is much more consistent. Okay, so that's what we're looking at here. Now, obviously what we're trying to do is to minimize standard deviation. So I always want to be down at the bottom of the best signals here. So from these two graphs, what I've chosen is 3 decisions. I want the move temperature, which is the big blue line, this one, to be at the bottom. So the big blue line, move temperature, on both CTQs should be at the bottom. Move temp, hold it to 40. Fix it, never move it again. Hold pressure, which is the green line. Want to be at the bottom of this green line. This one's not so big over here, but even so, the hold pressure, I want to be at the bottom of the green line. That's 10. And then finally the cool time. And the cool time, where are we? Cooling time is the brown line, this one here. I want to be at the bottom of the brown line, and that means being at 35. So the cool time goes to 35. Now what I'm going to do with those is fix them. I fix them because that will give me the best variability, the best standard deviation. Then I'm going to use the other variables to hit the target potentially. So let's look at the variables and the way that they hit the target. So if I go to the Y-bar graphs, of course this variable in particular, look, is the big one for hitting the target. I can also hit the target with the hold time, certainly in this particular instance as well. And of course the injection speed is also very influential in hitting the target. Now they're the graphs. Now really that's as much as you should do, and really what you should do is run a new experiment with these 3 variables in the experiment and run a full factorial. That's really what we should do, and that's what the client might have to do. But in order to save some time, we've decided to create a model out of the L12 to see if the model will work, and then we don't have to run the full factorial. So let's go back to the DOE, create the regression table, and let's see if we can use the models to try and understand the potential CpK. So let's go and do that now. Okay, so here we are. And this time the analysis we're going to do is not the marginal means plot, which we did last time. We're going to do regression. So if I hit regression, I'll get 3 models now side by side. I'll get the model for CTQ1, one for CTQ2, one for the cycle time. So that's what I've got now. Now, one of the things that we've got, CTQ1 unfortunately, hasn't got any good p-values in it. I'm going to take everything out of that model except the first variable. Now there's a reason why I'm doing this. I know 1 or 2 of the data points that I have actually are incorrect. My clients told me that, and they've actually told me that the fixed temperature is influential in CTQ1. So I'm going to leave that in the model, even though my p-value is telling me not to. I've got some extra data. They haven't sent me the updated version yet. I'll take the other poor p-values away from the other models, and I'll hit regression again. Okay, so now I've got the finished I've got the finished models, okay? So if you remember, I was going to hold the move temp at the hold pressure and the cool time. What I'm now going to do is ask the computer to optimize this. Now, in order to stop it moving certain things, I'm going to dial 40 into both boxes there for move temp. What's the other one then? It's the holding pressure. So the holding pressure should be a 10 in both boxes, and the cooling time should be at 35 in both boxes. Now that stops the computer from moving them, because in real life I want them fixed. And now I'm going to ask the computer to try and hit the target. Now the target, CTQ1, is equals to 423. Add the objective. CTQ2 is 198. Add the objective. Now that's all I'm going to put in there. I'm not going to ask it to optimize the cycle time, because I think that will confuse the optimizer a little bit too much. So I'm just going to ask it, go and optimize those two CTQs. Let's see what it comes back with. Okay, so it's telling me, well, in these cases here, it's telling me it can hit both of those. Let's see, settings to worksheet, see what it really says. So it says, if I blow this up, these results here, look. It says you can hit 422.8 with a standard deviation of 0.1893. You can hit 198 with a standard deviation of 0.1879. So in other words, what it's telling me is I can hit one of the CTQs dead on, but I can't hit CTQ1 dead on. Now I happen to know that CTQ1 has got a plus or minus 1 millimeter tolerance. So it's quite big. So actually this might not be a problem. The 198 CTQ on the other hand has got half that tolerance, plus or minus half a mil. So more difficult. So maybe we need to hit the CTQ2 more than we need to hit CTQ1. And you can see the cycle time. We're going to hit 59.63 on the cycle time. Now that's not great. They really don't want that 59-second cycle time. That's quite slow for them. So at the moment, we're picking a cycle which is going to be good but slow. So let's work out the CpK for that. So I'm just going to write down those numbers first so that I can then put them into the CpK tool. So let me just write them down. 198 with 0.88, that'll do. Okay, so let's take the numbers and make a prediction. So if I go to SPCXL, CpK, create the CpK with manual entry. Next. Then I put in the mean, which was 422.808 with a standard deviation of 0.189. We have a lower spec of 422. We have an upper spec of 424. Finish. Okay, now that's the capability. So that looks very good. Now we're off center. We're off center, that's the best the model could achieve. But you can see we're off center, but actually we're in good shape. We actually have, if I take the CpK and multiply by 3 there, what do I get? I get a sigma level of 4.2, which is very, very good. So that's CpK. That was CpK1, CTQ1 rather. So let's do the same thing now for CTQ2. Analysis diagrams, CpK, manual entry, next. Dead on the target, 198, with a standard deviation of 0.188. Lower spec is 197.5. Upper spec is 198.5. Finish. Now you can see with this particular situation, we're not as capable, but because we're dead center, we've got the minimum defect rate. Now this is the minimum defect rate you can achieve using this model. That's the prediction of the CpK. So what we've done is we've optimized for quality, but we've lost on the cycle time. Because if I go to the table, you can see my cycle time prediction, 59.63 seconds. Now this client doesn't like this. They don't like this number. They do like to have some capacity, and getting this like this would mean losing capacity because they're going to run much slower. So let's go to the cooling time, which clearly is heavily influential. Now the cooling time I locked off, if you remember, to 35. So that's the bad end of the setting as far as cooling time is concerned. I'm going to change it now in the yellow fields to 15. We'll get some new numbers. Now what we've got, look, is we've got 197.49. So we're off target, but more to the point. Look at the standard deviation. The standard deviation now is 3 times bigger. Now that could prove a real problem. But of course, I can do exactly the same thing. I can put those numbers into the CpK tool, and we can take a look and we can decide whether that particular result is more preferable to the result we've got now. So let me just write those numbers down. 422, 808, with a standard deviation of 0.27, 197.49, with a standard deviation of 0.56. So let's go and try those. Analysis diagrams, CpK, manual entry. Let's do the first one. 422, 808, with a standard deviation now of 0.27. So let's see what that comes out. Let's see what that comes out to. Lower spec, 422, upper spec, 424. Let me get that right first. Okay, now that's not bad. So we're off center, we got more standard deviation, but it's not destroyed our capability too much, but I think the other one's going to be the painful one. Let's take a look at CTQ2. Analysis diagrams, CpK, manual entry. Now we're putting in 197.49, standard deviation 0.56. That's a hell of a lot different to before. 97.5 at the low spec, 98.5 at the high spec. Click finish. Now look what we've done to the CpK by running faster. You know, I know we're off center. We could probably center that. We could ask the optimizer to center that for us. But even if we centered it, you know, look at the CP here. The capability here is only, the capability here is only 0.29. So regardless of what we do, we haven't really got a good situation. So although we could run faster, we will bang an enormous defect rate through the CpK2 according to our model. Now, you can make a business decision based on this. It's up to you which one you think's the best. To be honest, it looks like being defect free and running at 1 minute cycle time is going to be the best choice, because quite honestly, you're going to have to run 3 times faster. Of course, if you've got a defect rate as heavy as that, you're going to have to run the machine 3 times faster to keep up. So let's just take a look. Where's my regression table again? You know, the best cycle time, there it is. The best cycle time, look, I was only knocking 40 seconds off it. Well, I'm going to have to run double, triple the number of parts in order to get the parts out at the required speed. So, to be quite honest, it's an effective cycle time of about 120 seconds with the reject rate built in. So actually, the effective cycle time, the best one, is running at a minute with the lower defect rate. And that's obviously the choice that we would be making. Okay, so there is the CpK choice. Using DOE, we were able to see that one of the CTQs slightly off center but in good shape. The other one filling the tolerance. The cycle time equaled 59 seconds. And it's clear that that is the best choice. Now, as I say, a computer couldn't deal with this. AI couldn't deal with this. It doesn't know the price of anything. It doesn't know the customer. You know, it could be that for the particular customer, because you want on-time delivery for this customer and because they're very important to you, you might take the defect rate on the chin. There's all sorts of reasons why you would take scenario 2 as a better choice than scenario 1. But those reasons are personal to the job, to the customer, to the cost, all kinds of things, to your capacity. Things that, you know, a computer, there's just too much going on. You would spend a year programming the computer before it could figure out the right decision. Whereas if you use a DOE, it's very simple. The information's in front of you. Just run the scenarios. You can run 3 or 4 scenarios. You know the cost of these scenarios, and you can make a decision within a couple of hours that AI could never cope with. So there is design of experiments predicting CpK. Now, obviously what you've got to do, and this is what the client is doing, they are going away, they are going to run 50 of these, 50 of these, and they're going to see if that happens, because obviously that's a model. Models don't mean anything unless they reflect reality. So does the model reflect reality? Now, if it does, we don't have to do the second DOE. But if the model doesn't work properly, and the reason why it won't work properly is because none of the interactions are present. So we can't see any of these interactions. Do the interactions heavily affect the result? At this point, we don't know, because we haven't done the DOE to get that knowledge. But if these aren't influential, if they're not influential, then we're good. It doesn't matter, and we've got away with a cheap DOE. So we'll find out. But we're going to do a confirmation test, and we'll see what happens. But the idea of this little video was to show you, look, once you've got a DOE, you can play tunes with the CpK. You can decide speed or quality. By the way, as long as you collected the data that way, that would be really important. So speed or quality, predict the CpK. No other tool can do this. This is the fastest way to find out and make more money.